From the moment we're old enough to begin understanding the world, we're told something strange, that the Earth, this massive stable surface beneath our feet, is actually a sphere, spinning in space, orbiting around a great big nuclear fireball in the sky, located 150 million kilometres away. But if that's true, why doesn't it look or feel that way? Just look around. The ground looks flat, the horizon looks flat, buildings don't tilt, water doesn't appear to curve. So why are we so sure that the Earth is round? What's the actual evidence? Is it just something we've been taught? Something we believe because everyone else does? Or is there something deeper? Could it all be a big mistake? Or worse, could it be a lie? In this video we're going to find out. No appeals to authority, just light, shadows, and high school geometry. We'll retrace an experiment first performed more than 2,000 years ago, using nothing but a stick, a well, and the sun. And then we'll put the flat Earth model to the test, not with opinions, but with maths. This is not a thought experiment. This is measurable, observable reality. So let's begin where the ancient story starts, in Egypt. More than 2,000 years ago, Eratosthenes, a Greek scholar and librarian in Alexandria, did something remarkable. He estimated the size of the Earth. His experiment is elegant and famous, but it also reveals something deeper. It requires that the Earth is a sphere and that the Sun is significantly larger than the Earth and located hundreds of millions of kilometres away. So let's take a closer look. Around 240 BCE, Eratosthenes heard something curious about the city of Syene, what is now modern-day Aswan, in southern Egypt. On the day of the summer solstice, it was said that at noon, the sun shone directly down into a deep well, with sunlight illuminating the water at the bottom, and a stick placed vertically in the ground cast no shadow. This meant that the sun was directly overhead. But in Alexandria, further north, the same thing did not happen. At the exact same moment, a vertical stick did cast a shadow. So what's going on? That small discrepancy lit a spark in Eratosthenes' mind. If he could measure the length of the shadow in Alexandria, he could calculate the angle between the stick and the sun's rays. And then, by combining this angle with the distance between the two cities, he realised something astonishing. Using basic geometry, he could estimate the circumference of the entire Earth. Now, that's a bold and remarkable leap, so let's unpack it. First, it's important to understand that by Eratosthenes' time in the 3rd century BCE, the idea that the Earth was round was already well established amongst educated Greeks. This wasn't some radical or fringe belief, it was the prevailing scientific view, with deep philosophical roots and increasingly strong observational support. The idea likely originated with early philosophers like Pythagoras and Parmenides, who reasoned that the sphere was the most perfect harmonious shape, and thus a fitting form for the Earth. But it was Aristotle, a century before Eratosthenes, who provided clear empirical arguments. For example, travellers moving north or south noticed that different constellations gradually appeared or disappeared below the horizon, suggesting a curved surface. And during lunar eclipses, the Earth's shadow on the moon is always circular, regardless of the Earth's orientation, a phenomenon that only a spherical object can consistently produce. And it was widely reported that ships vanish hull first over the horizon, just what you'd expect if the surface was curved. So when Eratosthenes began thinking about shadows and angles, he wasn't starting from scratch. He was building on a well-established worldview, grounded in both logic and observation, in which the Earth's roundness was already accepted. Even when a story seems straightforward, how do you know you're really getting the full picture? Take the June 16 story, where astronomers from Harvard's CFA and Caltech mapped the distribution of ordinary matter across the universe, a big deal in cosmology. Over 30 outlets covered it, but not all in the same way. That's why I use Ground News, a website and app founded by a former NASA engineer who brought the same level of precision she used up in space to how we consume information down here on Earth. They let you easily compare how different media outlets report on the same story, while also showing you their political bias and factuality. Especially with stories like this, it's important to see more than one perspective. And if you're into science and physics, Ground News has dedicated topic pages so you can follow what matters to you without the noise. That's what ground news offers, a way to challenge assumptions, explore multiple perspectives, and ultimately think critically about the world we're shaping. So to see the full picture, go to groundnews.com/physics, scan the QR code or click the link in the description. You'll get 40% off the Vantage plan, which is just $5 a month, and it will help support this channel. Okay, so let's get back to the physics. But there's another key idea built into Eratosthenes' method. Imagine placing a bright light source just above the Earth. Its rays would spread out in all directions, hitting different parts of the surface at very different angles. But now imagine lifting that light source higher and higher, further and further away. As the distance increases, the rays become increasingly parallel at the Earth's surface. This is exactly the principle Eratosthenes relied on. The idea that if the Sun was suitably distant from the Earth, that rays of light would be essentially parallel to each other when they reached the Earth's surface. A few decades earlier, Aristarchus of Samos had established the relative distances to the Sun and Moon. He concluded, correctly though with underestimated numbers, that the Sun was vastly farther away than the Moon and far larger than the Earth. This insight had a crucial implication. Sunlight reaching Earth could be treated as essentially parallel rays. And that mattered enormously, because it provided an explanation for the fact that at noon on the summer solstice, a stick placed vertically in the ground in Syene cast no shadow, but at the same time in Alexandria further north, a stick placed vertically in the ground did cast a shadow. The explanation was that the surface of the Earth was curved. And this brings us to Eratosthenes' remarkable insight. He measured the angle between the rays of light and the stick, known as the zenith angle, at Alexandria, and found an angle of 7.2 degrees. Now here's the clever bit. He realised that if the Earth is a sphere, and Alexandria and Syene lie along the same north-south line, then that 7.2 degree angle corresponds to the angle subtended at the Earth's centre by the arc between the two cities. By dividing 7.2 degrees by 360 degrees, Eratosthenes could determine what fraction of a full circle lay between Syene and Alexandria. He realised that this same fraction must also apply to the arc distance between the two cities, which we'll call d, and the full circumference of the Earth, which we'll label c. And so he realised that d divided by c must equal 7.2 divided by 360, which is approximately equal to 1/50. And therefore, according to Eratosthenes' calculation, the circumference of the Earth must be roughly 50 times the distance between Alexandria and Syene. So the natural question was, what is the distance from Syene to Alexandria? Now, Eratosthenes knew it was about 5,000 stadia. This figure was likely based on records from professional beamatists, trained surveyors who measured distances by counting their steps along established routes. The stadian was a Greek unit of length, and while its exact value varied, modern estimates place it at around 157.5 metres. It then follows that the full circumference of the Earth is going to be 50 times 5,000 stadia, which is roughly 250,000 stadia. And converting this into kilometres, we find an estimate of around 39,375 kilometres. And if we compare that with the modern day measurement of Earth's circumference, we see that Eratosthenes was remarkably close given the crude methods of measurement available at the time. Okay, but what happens if you repeat this approach with different cities? Eratosthenes used just 2 cities, but what if we repeat the same idea with dozens of cities from the equator all the way to the North Pole? Let's now consider this in detail. We'll begin with the recap of how latitude is defined for the Earth. If we assume the Earth is spherical, and then draw in the rotation axis of the Earth, and label the North and South poles, then the equator line intersects the rotation axis at an angle of 90 degrees. We then use the equator as our reference line, and label its latitude as 0 degrees. We can then determine the latitude of any location by measuring the angle subtended at the centre of the Earth by the arc along a meridian from the location to the equator. So, for example, New York City is at a latitude of roughly 40 degrees north, and Oslo is at a latitude of roughly 60 degrees north. Using this approach, we would define the latitude of the North Pole as 90 degrees north, and the latitude of the South Pole as minus 90 degrees, or 90 degrees south. Okay, now to make our calculation as simple as possible, we're going to imagine that it's the equinox, which occurs around the 20th of March or September 23rd, because on this day, at the equator, the sun is directly overhead at noon, and this will make our calculations significantly neater. For example, let's for a moment consider a city such as Ankara in Turkey, which has a latitude of roughly 40 degrees north of the equator. We can mark this angle on our spherical globe. If we then imagine placing a stick in the ground and measuring the angle between the stick and the sun's rays at noon on the equinox, we would find an angle of 40 degrees. And if we look at the sky, we would see that the sun will be 40 degrees south of overhead. We would say that the zenith angle is 40 degrees. And this angle exactly matches the latitude of Ankara. And if we took a city directly south of Ankara on the equator, such as Kampala, with a latitude of 0 degrees, then the sun would be directly overhead, and a stick would cast no shadow, and the zenith angle would be equal to 0. And finally, if we consider the North Pole with a latitude of 90 degrees relative to the equator, then the sun will just skim the horizon, and so the angle between a stick placed in the ground and the light ray would be 90 degrees. And if we repeat this for any location between the equator and the North Pole on the equinox at noon, and record the latitude and zenith angle, we will find that the latitude will exactly match the zenith angle for all locations. And furthermore, if we repeated for southern latitudes, we would find the same relation, only with a negative sign in front of the latitudes. And so we arrive at a beautifully simple rule. The zenith angle at noon on the equinox is equal to the absolute value of the latitude. And we can see this most clearly if we plot latitude on the horizontal axis and zenith angle on the vertical axis, and we get a perfect V-shaped graph. And real-world measurements match this prediction beautifully. And this, if you think about it, is a very simple theory to test. You simply need to place a stick in the ground at different latitudes on the equinox, and then by measuring the length of the shadow and the angle between the sun and the stick, you can then compare with the latitude of the location. If they match, then that is very strong evidence supporting the round Earth, faraway sun theory. Okay, so now that we have a rule connecting zenith angle to latitude, we can use this to estimate physical distances between cities on the surface of the Earth. As we've already discussed, using the shadows cast by sticks, we can estimate that a round Earth would have a circumference of around 40,075 kilometres using modern day estimates. And since there are 360 degrees in a circle, that means each degree of latitude corresponds to 111.3 kilometres per degree. This gives us a quick way to translate latitude into real-world distances from the equator. For example, Kampala sits at 0 degrees latitude right on the equator, so its distance from the equator is, by definition, 0 kilometres. Ankara, at 40 degrees north, lies about 4,452 kilometres away from the equator, and the North Pole, at 90 degrees, is roughly 10,017 kilometres from the equator. These aren't just numbers on paper, they're real distances. Distances you can measure. Pick any two cities along the same north-south line, calculate the latitude difference, and multiply by 111.3 kilometres per degree, and then check it in the real world. You can drive it, fly it, walk it. However you choose to measure, the physical distance matches the prediction. And this is where it gets interesting. Even if you believe in a flat Earth, you still have to accept these measurements. Yes, you might disagree on exactly how many kilometres, there may be plus or minus 5, 10, 15, 20, but the order of magnitude you have to agree on. For example, if you travel from Kampala to Ankara, for instance, you'll find with your odometer, your GPS, or a very long tape measure that the distance is indeed around 4,452 kilometres. That gives us a common foundation, agreed upon distances that both models must account for. So now we can go and put them to the test and see which one actually works. But the first thing we need to do is to understand why the observations of Eratosthenes that different locations on Earth will cause different length shadows is an issue for a flat Earth model. You see, in the round Earth model, the Sun is extremely far away, about 150 million kilometres, and as we've already seen, that means rays of light arrive at the Earth's surface essentially parallel. But if that's true, then the only way to explain differences in shadow angles between two locations is for the surface itself to be curved. That's exactly what Eratosthenes showed us. Flat Earth proponents reject this idea. They argue that if the Sun were very far away, then because the Earth is flat, all locations should see the same shadow length and same angle between the Sun's rays and sticks placed in the ground, and shadow differences would make no sense. So instead, they propose that the Sun is much closer, and that the different shadow lengths are due to the fact that the rays are not parallel at the surface, and we can see this explicitly from the animation. Okay, so let's take this idea seriously for a moment and think about testable consequences of such an idea. We'll refer back to the two cities we mentioned earlier, with Kampala located at the equator and Ankara located 40 degrees north. Now, it's an experimental fact that both flat earthers and round earthers can both agree on that at noon on the day of the equinox, a stick placed in the ground at Kampala on the equator will cast no shadow, whilst a stick in the ground at Ankara will cast a shadow with an angle between the sun's rays and the stick being 40 degrees. And here is the key point. The way that the flat earthers will attempt to explain this is by saying that the sun is actually much closer to the surface of the earth, such that a ray of light can cast no shadow at Kampala, but at the same time a ray incident on Ankara will make an angle of 40 degrees relative to a stick placed in the ground, and hence cast a shadow. And so it appears the problem is solved. The earth is actually flat. But wait, let's actually follow through the logic. Can we calculate how close the sun must be in order to recover the correct shadow lengths at Kampala and Ankara at the same time? Well, if we take our diagram showing the two sticks in the ground at Kampala and Ankara, with the sun directly above Kampala, then a light ray will cast no shadow at Kampala, but will cast a shadow at Ankara, and the angle between the ray and stick will be 40 degrees, and this is also the angle made between the two rays on the diagram. And we see that we have a right angle triangle. If we label the distance between Kampala and Ankara as d, and the height of the sun above the Earth's surface as h, we can then use the fact that for a right angle triangle, the tangent of an angle is equal to the length of the side opposite the angle divided by the side adjacent to the angle. If we apply this to our situation, we have that tan of 40 is equal to d divided by h, and therefore h is equal to d divided by tan 40. And so this equation is telling us how high the sun has to be in order for us to be able to explain what is actually observed. Now, if we use the distance between Kampala and Ankara that we estimated earlier of 4,452 kilometres and sub this into our equation, then we see that the sun must be at a height of around 5,300 kilometres for the flat Earth model to work. For comparison, the round Earth heliocentric model puts the sun at a distance of roughly 150 million kilometres from the Earth, so quite a big difference in what the two models are claiming about reality. Okay, but let's keep an open mind and keep working with the flat Earth model for a bit longer. After all, I've just shown you how a flat Earth model with a nearby sun can apparently explain the difference in shadow length between Kampala and Ankara. So the next step is to treat it like any fledgling theory in science and use this model to make a new prediction which we can then test. For example, if we were to continue heading north from Ankara and you kept walking, you would eventually end up in Murmansk in Russia, which has a latitude of close to 69 degrees. And if we measure the angle between the sun's rays and a stick in the ground at noon on the day of the equinox in Murmansk, we find an angle of 69 degrees, which matches the angle of latitude, and also matches the predictions of the spherical Earth model. So the question is, what would the flat Earth model that we used earlier predict? Well, given that the distance between Kampala at the equator and Murmansk is around 7,680 kilometres, and using the flat Earth height of the sun value of 5,305 kilometres that we calculated earlier, we can now ask the question, what is the predicted angle theta according to the flat Earth model? To answer this question, we can use simple trigonometry. We can construct a right-angled triangle with a base length equal to the distance between Kampala and Murmansk, a side length equal to the height of the sun, with theta representing the predicted angle that the sun's rays would make with a vertical stick placed in the ground, aka the zenith angle. We can then use the fact that tan of theta is equal to d over h, and if we sub in the numbers from our diagram, we find that tan of theta is roughly equal to 1.448. We can then determine the predicted angle theta by calculating the inverse tangent of 1.448, which is equal to 55.4 degrees. So there it is, nowhere to hide. That is the prediction we arrive at when we use the flat Earth model that correctly accounted for the shadow angles in Kampala and Ankara. And we have now predicted what that same model says about Murmansk, and it says that the angle between the sun's rays and the stick should be 55.4 degrees. And we can test this prediction. We simply place a stick in the ground in Murmansk on the day of the equinox at midday, and we measure an angle of 69 degrees, not 55.4. That's a discrepancy of over 13 degrees. Nowhere to hide, nowhere to run. The flat Earth model gets the predicted angle wrong. We can see the failure of the flat Earth model most clearly if we plot the relationship between the zenith angle, the angle between the sun's rays and a vertical stick, and the latitude for both the spherical and flat Earth models. As we've already seen, the spherical Earth model makes a clear prediction that, at noon on the equinox, the zenith angle is equal to the absolute value of the latitude at all locations. But what about the flat Earth model? Can we generalise this model? Well, if you recall, each degree of latitude corresponds to a surface distance of approximately 111 kilometres, and we've also seen that according to the flat Earth model, the zenith angle theta is related to the horizontal distance from the equator, which we'll call d, and the sun's height h by the equation tan of theta equals d over h. Now, if L is the latitude in degrees, then we can write the distance d as 111 times L. Substituting this into our tangent equation gives tan of theta equals 111 times L divided by h. And so, to ensure the zenith angle is always a positive value, we take the magnitude and write the general expression in the following form. If we now sub in the values for the height of the sun, we arrive at the following equation. This gives us a direct relationship between the zenith angle and latitude in the flat Earth model. We can now plot both this curve and the spherical Earth prediction to compare them directly. Just to reiterate, the spherical Earth model predicts a linear relation between the zenith angle and latitude, whereas the flat Earth model predicts a non-linear relation involving the inverse tan function. If we begin by plotting the spherical Earth prediction, we find the following dashed blue line. And if we then plot the flat Earth prediction, we find the following orange curve. We clearly see that the flat Earth model only agrees with the spherical model at exactly 3 points: 0 degree latitude, where the sun is directly overhead, and plus or minus 40 degrees, with one of those being Ankara, which we use to calibrate the model. The agreement at minus 40 degrees isn't a success. It's simply a consequence of symmetry, since it's the same distance from the equator. But beyond these 3 points, the flat Earth model fails, and fails badly. Now, you might think that this is just because of the cities we picked, but it's not. We could have picked any other city instead of Ankara, say one at 20 degrees or 60 degrees, and tuned the flat Earth model to match that, and we'd always get the same outcome. The model would match the zenith angle at just 3 latitudes, the equator, that chosen latitude, and its symmetric counterpart, but it would fail everywhere else. And this is the hallmark of a bad scientific model. It doesn't generalise, it doesn't explain, it just retrofits, and it breaks the moment you step outside the data it was crafted to match. In contrast, the spherical Earth model makes a simple, bold prediction that on the equinox at local noon, the zenith angle is equal to the absolute value of the latitude. And it gets it right, not just in Kampala and Ankara, but in Murmansk, at the North Pole, and everywhere in between. This is the power of a correct scientific model. It doesn't just work in one specific case, it's generalizable, it's accurate, and it's universal. And it harmoniously connects and reinforces other things that we've discovered about the universe, such as the universal law of gravitation, the heliocentric model of the solar system, the fact that the Sun is 150 million kilometres away and vastly larger than the Earth. But that's not what flat earthers will tell you. They think the Sun is just over 5,000 kilometres above us. And so let's be patient and kind, and even though we have already shown why it's wrong, let's take this idea seriously for just 5 more minutes, for entertainment purposes, and because we can always learn more physics by revealing the problems with this picture. If we imagine drawing 2 lines connecting either side of the Sun and tracing it back to the surface of the Earth, then the angle between these 2 lines is around 0.53 degrees. In other words, this is the measured angular size of the Sun in the sky, which both flat earthers and round earthers can all agree on, as it's very straightforward to measure. Now the question is, given that flat earthers believe the Sun is 5,305 kilometres above the surface of the Earth, and given that the Sun's angular size is 0.53 degrees, what is the diameter of the Sun according to the flat Earth model? To answer this question, let's bisect this angle. We can then make a right-angled triangle with one side being equal to the height of the Sun above the Earth, which we label h, and another being equal to the radius of the Sun, which we label r. Now, if we focus in on this triangle, then the bisected angle is 0.265 degrees, and then we can use trigonometry to write tan of 0.265 equals r over h. Then, since the diameter of the Sun will be equal to twice the radius, we can write the diameter as 2h times tan of 0.265. And then, if we sub in the height of 5,305 kilometres we calculated earlier, we find a Sun diameter of 49 kilometres. And so there we have it. According to the flat Earth model, that great big nuclear fireball in the sky that we call the Sun is actually only 49 kilometres wide, at a height of just over 5,000 kilometres above the surface of the Earth. To put that in perspective, imagine that we zoomed in and hovered over the region representing Greater London in England. Now, according to the flat Earth model, the Sun would just about stretch across this area. In other words, the Sun is tiny. And just to emphasise, this is the diameter that the Sun must be in order to simultaneously account for its appearance in the sky, and the fact that it's apparently only 5,300 kilometres above the surface. Again, there is nowhere to hide. This is what the model predicts. But it doesn't take a genius to realise that there are several catastrophic issues with this model, and for the sake of time and our sanity, we will just briefly mention 2. Firstly, if the Sun is always the same distance above the flat Earth, how does it ever set? And secondly, if the Sun moves in a circle above the flat Earth plane, wouldn't its size in the sky change as it moves? The simple fact is this: if the Sun is just 50 kilometres across and hovers 5,300 kilometres above a flat Earth, moving in a circular path above the surface, then basic trigonometry tells us 2 unavoidable truths. First, the angular size of the Sun in the sky would visibly change as it moves towards or away from an observer. And second, it would never dip below the horizon. Instantly, flat earthers are faced with 2 fundamental problems. To explain them away, they must resort to ever more implausible fixes, each of which only creates new contradictions elsewhere. The problem becomes clearer if we imagine the Sun maintaining a fixed height as it moves further from the observer. As it recedes, the angle between the Sun and the ground, its apparent elevation, gradually decreases, and as with any object moving further away, its angular size shrinks. But here's the catch: for any finite-sized flat Earth, the angle never reaches 0. The Sun never touches the horizon. No sunset, ever. So let's push this to its extreme. Suppose we make our hypothetical flat Earth enormous, say 200,000 kilometres across. Even then, the sun only approaches the horizon. It never quite gets there. And now flat earthers face a new dilemma. Yes, a wider disk brings the sun closer to the horizon, but it also means the sun's apparent size must change drastically throughout the day, growing and shrinking as its distance varies. Have you ever seen the sun swell or shrink in the sky this dramatically during the day? No. No, you haven't. Because it doesn't. And the inconsistencies only multiply from here. But if you've made it this far, I suspect I've already tested your patience with flat earth logic. I'm sure I'll receive a flurry of constructive rebuttals when this video goes live, and I welcome genuine discussion. If you want to help, please join in by pointing out the flaws in flat earth reasoning with calm, evidence-based explanations. But to any flat earthers still watching, please consider this. The very science that clearly demonstrates the Earth is spherical forms part of a framework. From gravity to geology to thermodynamics, fluid dynamics, relativity, quantum mechanics, it's the same science that lies at the heart of every part of modern life. From GPS satellites to airplanes, engines, smartphones, the internet, all of it runs on that same scientific framework. So when you reject a spherical Earth while using the tools that rely on relativistic corrections and quantum engineered semiconductors, you're contradicting yourself. Because you're relying on the results of a system you claim not to believe in. So if you truly think that the Earth is flat, then be consistent. Put down your phone, switch off your computer, disable your GPS, and stop using the internet. Otherwise, you're a hypocrite. Be true to your belief. Walk into the wilderness and refuse to ever use the technology created by scientists ever again. So thank you for watching, and until next time, goodbye. And as always, a massive thank you to all my patrons, and a special shout out to the following who have been incredibly generous with their support. Thank you so much. I couldn't do it without you.